Hi, I'm Osan. I will present our work on 3D common corruptions and data augmentation. As shown many times before, computer vision models are brittle in the real world due to distribution shifts from training data. Here we show this for a surface normals model. The input image has a change in focus. The chairs at the right are in focus and the rest of the scene is blurry and out of focus. Under this change, the scene geometry is still obvious to a human, however the model predictions decrease significantly. Note that the blur is not even generated adversarially, and it's a distortion that can be faced in the real world commonly. This poses a critical problem that needs to be solved before deploying these models in the real world. Common corruptions benchmark has been proposed to evaluate models against several distribution shifts. These shifts are obtained by applying different corruptions over the image, such as Gaussian noise and defocus blur. While it provides a useful tool to understand model vulnerabilities, it only considers simplistic 2D modifications over the images. In other words, common corruptions do not take scene 3D into account. This results in corruptions that could be unrealistic. In this work, we consider a different approach. While generating the corruptions, we incorporated the 3D information and real-world scene properties. The outcome is a diverse set of realistic corruptions ranging from motion blur to lighting and occlusion changes. For example, 3D motion blur at the top obeys motion parallax. See the chair at the end of the corridor having less blur than the walls nearby. This is in contrast to 2D motion blur below applied uniformly everywhere. Similarly, the 3D defocus can change scene depth of field and focus region. Illumination changes take the scene geometry into account and generate shadows. Likewise, fog gets denser with more distance. In the 3D case, occlusions also occur naturally, for example, plant occluding the fridge here. This is possible in our case by placing the camera in the scene in a particular way so that the one object occludes the desired object by a desired ratio as shown here. Note that this is quite different than the commonly used 2D occlusion at the bottom that drops random patches, which is unnatural. This is an example of a new class of corruptions that we introduced in this paper, called semantic corruptions. In total, we created 20 different corruptions, which we named as 3D common corruptions, or 3DCC in short. They address different aspects of real world, such as depth of field, semantic changes, weather, lighting changes, view changes, motion blur, video-based artifacts, and noise. Overall, 3DCC has a diverse set of distribution shifts. What is the significance of these corruptions? In this work, we use them for two purposes. The first one is to create a benchmark to test robustness. 3DCC is a challenging benchmark for models. Further, it exposes vulnerabilities that are not captured by the 2D corruptions. Now let's look at some example results. See the errors made by a surface normals model against the motion blur with increasing intensity. The rightmost plot shows the increase in the L1 error. Similarly, for near focusing, the errors increase significantly and non-uniformly throughout the scene. Likewise, see the performance of a detector model against occlusion corruption we showed before. When occlusion ratio is above 25%, performance drops severely as shown in the accuracy plot at the right. Our method allows performing such occlusion analysis for different objects in a realistic way. Besides benchmarking, the second use case of 3D corruptions is data augmentation. If 3D corruptions are indeed similar to the ones in the real world, it's a natural question to ask whether we can robustify a model using these corruptions as data augmentation during training. The answer is yes. This resulted in significantly improved robustness compared to baselines, both qualitatively and quantitatively. We consider surface normals models trained on taxonomy and omnidata. Our model starts from the omnidata one and uses 3D augmentations. You can see more results or try your images in the live demo in the project page. The predictions are obtained frame by frame on sample YouTube videos. The frames often exhibit large distortions due to camera motion and compression. Our model is notably more accurate and consistent. It also produces predictions with less flickering. Overall, using 3D augmentations notably improve robustness against real-world distribution shifts, especially for those depending on 3D. Finally, we show that 3D corruptions can be applied to standard vision datasets. Note that one needs depth to generate 3D corruptions, while most datasets such as ImageNet and COCO don't have those levels. Hence, we use depth predictions from an omnidata model to generate the corruptions, as shown here. For example, with this approach, we can perform near focusing on ImageNet samples, or we can apply fog on COCO images. Motivated by this, we introduce ImageNet 3DCC benchmark. It's also a part of the robust bench now. Thank you for your attention.